Hi, kids. So we're going to get started right away with some notes, and then we'll move on from notes to finishing up those optimization problems. I think it's ready for Tuesday. And then we'll be good to go. Day 39 homework, which will be the homework at the end of this lesson, unfortunately will be due on the day of the final because I can't carry grades over in the second semester. So just knock it out and you'll be fine. When we're done with the lesson then today, you've got a couple options. One option would be obviously to get the help with the optimization problems you might have. You can also work on this day 39 assignment. And I think I've posted, if I haven't, I will post the FERP for you to take a look at. Okay, and we'll talk a little bit about that later. There is a slideshow if you want to use it for this. It's entirely up to you. I keep looking at that double screen. It's wigging me out. I'm going to turn around. Okay, so we're talking about antiderivatives. What are antiderivatives? It's exactly what it sounds like. It's the opposite of a derivative. Right? Pretty clever that way. So, we're going to do general solutions of differential equations. That sounds scary. It's not bad. We're going to do something called an indefinite integral, which is another term for an antiderivative, and learn some notation. We're going to get a new symbol today. This will be exciting. And then we're going to do some basic integration rules. Integration, antiderivatives, and indefinite integrals are all terms that mean the same thing, doing the opposite of a derivative. And then we're going to do some partial solutions. That'll make sense again when we get to it. But let's dive right in. So I have a simple question for you. Suppose I have a function, 3x squared. You can all take the derivative of that, yes? What is it? Just wanted to make sure. The final's looking good for most of you. Excellent. However, there is a function that when I took the derivative of that function, I got f of x. In other words, I got 3x squared. What is that function? No. X cubed. Right? Everybody with me on that? If you're not sure, then take the derivative of x cubed. What's the derivative of x cubed? 3x squared, we're good to go. You just did your first antiderivative. Way to go. High five yourself. Excellent. Okay, so there's some notation. Now notice I introduced capital F. So we're establishing a line of antiderivatives slash derivatives, and that is, we've talked about up to this point about f of x, f prime of x, f double prime of x, f triple prime of x, et cetera, but now we're going to go backwards. And when you go backwards from f of x, you get capital F of x. Okay? Any problems so far?
You gave him the no. Stop. That was like fully done.
Thank you.
Wait, I do actually have a question. So like, how do you know that's right? Because like, can't that also like the derivative, the like antiderivative of that be like x cubed, but like also like any constant like ever? Huh.
Hold it.
Genius Liz.
Wait for it. You mean like x cubed plus 7?
Yeah.
Or if you're feeling saucy, x cubed minus 12?
Yeah.
Excellent question, and the answer is yes, there are a lot of them.
Yeah.
It is called a family of solutions, or a family of antiderivatives. There are an infinite number of functions that when you take the derivative of it gives you 3x squared. This gets a little confusing because when we took derivatives, there's only one answer. The derivative of x cubed is 3x squared. Done. But when you go backwards, as Liz mentioned, aren't there a lot of different functions? And the answer is yes. How do we represent that? We use a plus c. That's a capital C, and capital C stands for a constant. The technical term for that is a constant of integration. When you're doing this antiderivative process, you have to include that constant on everything. In a lot of AP questions, you will get an entire point for just writing plus C. Okay? Questions so far? Good. What's C plus C? No.
C.
C. What's C times C?
C.
C. What's C raised to the C power?
C.
C. No matter what you do to C, you're going to get another C. That will become relevant later on when we start looking at some problems, because you'll have multiple C's. But if you have multiple C's, then you know you can just add those multiple C's together to get a C.
What if it's like C minus C or C divided by C?
C minus C is still C.
What is that?
Nope.
What if you take the antiderivative of C?
Ooh, we'll get to that later. That's a good question.
Now we're thinking about user experience.
So, let's start with something simple. I have a derivative that I've labeled y prime. I would like to know the general solution. So that business, going back a slide, where we got capital F of x is x squared plus c, that's called a general solution because it encompasses an infinite number of possibilities. So in this problem where I ask you for a general solution, if you do it correctly, it should end in plus c. Okay, we're gonna start easy here. The simple question is, what function, when you take the derivative of it, gives you x squared?
1/3 x cubed.
Say again?
1/3 x cubed.
1/3 x cubed, yes? No, you forgot something.
Oh, plus C.
Plus c, right. There you go, 1/3 x cubed is the antiderivative, but you have to remember to include the plus c because there are, again, an infinite number of possible functions that will give you that. Everybody good? Oh, you got a squeaky chair. Okay, well, don't move. It's not making noise. You're doing a great job. So here's a picture of all the well, not all of them, a number of possible solutions for that antiderivative. And notice, you should remember this from basic graphing skills, adding a constant to a function, all it does is move it up and down. So each one of those pictures, red, purple, green, blue, black, and light blue, are all 1/3 x cubed that have just been moved up and down, depending on the C term that you use.
Are those cards are purple? It's blue.
No, red.
No, the 1 through 2 is purple.
What is it?
Is this purple?
Yeah, it's totally purple. You remember it. You guys remember that from the cartoons? What are you, a maroon? Yeah, it's purple. Yeah, you're wrong. Moving on. Okay, new symbol. You're gonna struggle drawing this symbol. Part of it will be practicing it. Okay, that squiggly thing is your new symbol. Some of you will draw it and make it look like a big fat S. Some of you will get fancy and do like a loopy little thing at the top and the bottom. I don't care how you draw it, as long as you don't draw it as a straight vertical segment. It's gotta look like an integral symbol. Why did I know you were gonna ask a question?
Can I draw a line with dot?
You can do whatever you want. This is America, but borrow it on. You just might have it marked wrong.
Drawing a line with the dot.
No.
No.
So notice, I'm defining the function y, or the value of y, as the antiderivative of f of x dx. That dx is important, which we'll get to in a second. And when I do that, I get a capital F function, because again, if we go backwards from f, we get capital F. And then you gotta remember to stick the plus c on there. That thing that you're taking the antiderivative of is called the integrand. The dx is the variable of integration. That becomes very important. The reason that dx is there is that it tells you, hey, my variable in this problem is x. It seems obvious, but it's relevant later on when we start getting into more complicated problems. It'll become relevant in a slide or two. That thing is the antiderivative of f, and then of course, as I mentioned already, you've got your constant of integration. What's that?
Will this stuff be on the plan?
No. Okay. So in red, you see I've got that indefinite integral thing. We've used a lot of new terms. Indefinite integral, antiderivative. There's another one Oh, integration, there, right, should have got the title of the chapter, right? Problem so far. Okay, got a couple small points to talk about, and then we're going to do example and example and example to make sure you understand what's going on. Okay, so here's some basic integration stuff. I'm gonna throw them both up here and then you can process the difference. Notice this first blue box is taking the antiderivative of a derivative and getting the function plus c. Right? So it's like taking the square root of a square. They undo each other. Integration undoes differentiation. Or an antiderivative undoes a derivative. Everybody with me? We're good? Okay, so why is this one different? Where'd the c go?
Would be 0.
Oh, Chris, I almost said expand. Chris, expand. Explain, please.
If you take a derivative of a constant, it equals 0.
Beautiful. In the first one, what did we do first? Anybody? Did we take a derivative or an integral first? Took the derivative, then we took an integral, plus c. In the bottom one, we took an integral first, then took the derivative. Okay. So that comes back around. Remember when I said whatever you do to c, you get c? That is kind of true, but what's the derivative of c? 0, right. The derivative of a constant is 0. That's why that's a fairly subtle point there of why there's no c for the bottom one. Are you with that?
Why don't we just do like the inverse notation, like normal inverse notation?
Well, it is inverse notation. Think about when a square root is an inverse of x squared, right? So why don't we just use an inverse notation there?
That makes sense.
Because it's more fun to have a new symbol
Yeah.
that nobody can draw.
No, that's what I was.
Okay, all right, good.
Yeah.
All right, good. Nice job, Chris, by the way. Okay. So let's talk about another one. Let's do x cubed. What's the antiderivative of x cubed?
To the 4th plus c.
Nailed it. Everybody hear that? Say it loud, say it proud to make sure the computer records that.
1/4 x to the 4th plus c.
Outstanding. Yes, you are. Luke?
Hi.
Can you, hi, now that we've established that, could you generalize what you just did so that we could do it for any polynomial? Let's say we're doing x to the 7th. What would be the antiderivative of x to the 7th?
1/7? Or, no, it'd be 1/8. Right, 1/8 x to the 8th plus c.
Good. What if we had x to the 12th?
1/13 x to the 13th plus c.
Excellent. What if you had x to the nth?
1/n plus 1. X to the n plus 1 plus c.
I don't even know why I'm here. I should just give Luke the clicker. Well done. Okay. Are we good? Okay, so now, Tori, you go home tonight. You have a little brother or sister? How old's? 12. Great. So you're sitting at dinner with your 12-year-old sister, and she says, "Hey, what'd you do at school today?" And you're like, "We did some integration." Well, what is that? How would you explain Luke's idea in simple English that you're fairly bright 12-year? I mean, I don't know. I don't want to make a judgment call. I'm just going to say your 12-year-old sister would understand. Hold on, before you answer, we'll assume that she knows what the exponent is and what the base of it, she knows what the x and the exponent are.
I'd probably say that you're trying to make the function larger than it is, so then you put a fraction in front of it, one over the previous exponent, and then x to 1 more on that, which is plus c.
So close. Say it again just to make sure I didn't mishear it.
Okay.
I don't want to have to roll role play your 12-year-old sister. I'm trying to ignore that because that would get really weird.
Okay, I say that you have to put a multiply the fraction, by the base of the exponent, one over the previous exponent plus one, then raise the base to one value more than the exponent plus c.
Bryce, if you were a 12-year-old sister, would you understand that? That's how your eyes roll back in your head. You're going to your happy place there for a moment. Are you good now?
Yeah, I'm good now.
Good. Try once more, please, for zone boy over here.
Okay.
Okay, focus. Come on, you got this, Bryce. Okay, imagine you're a 12-year-old sister. Okay, go.
Okay, so you have you have to multiply the base by the fraction of the new exponent. So the fraction would be one over the previous exponent plus one multiplied by x, which is the base, raised to one more than the previous power. So n plus one plus c.
How we doing, 12-year-old sister?
No, I don't know. That made no sense.
Say it one more time.
Yeah, one more time. If you say it one more time, maybe you'll. 12-year-old, I don't think I'll ever.
One more time.
No?
Yeah.
Probably n plus one more time.
As a 12-year-old, I think.
Anybody else? Luke, you started this mess.
Yeah.
Alright, take the exponent, add one, move it to the front, put it over one,
Would your
put it under one.
underwear? Sorry. Would your 12-year-old sister understand what a reciprocal is?
Yes.
Okay, beautiful. Back to you, Luke.
So smart 12-year-old.
Billy.
What was I?
I don't know. Start over. Take the exponent.
Okay, so you take the exponent, add one, move it to the front, take the reciprocal of that. And then you take the same number that you took the reciprocal of, make that the exponent, and then you add c.
We good?
Right, does that make sense?
Raise the exponent by 1 and multiply by the reciprocal of the new exponent. Same thing. Okay, well done. Good. So you should be able to find, if we're just dealing with basic polynomials, and you can kind of see where this is going, we're going to follow the same pattern we followed with derivatives with integrals. So you'll recall that this process is almost identical to what we did with derivatives. We started with very simple derivatives. How do you find the derivative of x squared? Well, you bring the exponent down, reduce it by 1. Okay, so that we have a basic integration rule that will work for basic polynomials. Now, what happens when we stick a number in front of it? Well, we did the same thing with derivatives. The number doesn't matter. Okay, so if I'm taking the antiderivative of 3x squared, the 3 just sits out in front. I take the antiderivative of x squared and then I multiply my answer by 3. The same thing is going to happen here. Okay, this is really important. That's why it's flashing. Now, I've got some good news for you, kids. It's such good news that I put it in a giant red thing and made it, I think
Santa Claus.
I think it flashes. Yes, Santa Claus. No, not Santa Claus. Oh yeah.
Let's go.
Okay, wait, I think it flashes too. Yes, it flashes. Now, I put it in a big red starburst. I made it flash. But you know what a number of you are going to do? You're going to forget and do a product rule for integrals. You're going to do a quotient rule or chain rule. You don't have to.
There's a catch to it.
No, there's no catch. Really, I would tell you if I had something sinister coming up. No, there's nothing else that's going to make you cry later on. This is just,
Ever?
I wouldn't say that.
Well, it's like it's not product rule, it's called product rule.
Yeah, so we use the Gaelic spelling.
Yeah. No, it's duck rule.
So, the problem is,
I know how to say it.
the problem is you're still gonna have to take the antiderivative of things that are products. So we're gonna have to come up with some creative ways to do that, because the product rule for derivative, there is no such thing. Okay. Now, some of that might be multiplying it out. Instead of doing a quotient rule, you might divide it. Chain rule, that's a whole nother animal. We're just gonna pretend that's not even up there.
Yes.
So here are some basic integration rules. And the chart is there because these all come from the simple question of what's the derivative, or sorry, what's the function that when you take the derivative of it, you get 1 over x? You know all these. I just put them together for you into a chart. So notice at the top, if my function is c times f of x, that's a constant times f of x, it's the antiderivative is simply that number times the antiderivative. The antiderivative of a sum is the sum of the antiderivatives. Addition and subtraction still work just like they did with derivatives. Everybody good to go? The third one down is what Luke told us about, the natural log. We've done that already. That's the opposite of u prime over u. If the derivative of e to the x is e to the x, then the antiderivative of e to the x is e to the x. We've talked about the when the base is not e, when it's a number, and then you've got some trig stuff in there. We're going to start small with the trig stuff with just those 4. We'll talk about tangent later, secant and cosecant, but for now you just got those. A problem comes up when now you've done derivatives for maybe since the middle of September, and now we're in the middle of December, so that's October, November. 3 months you've been doing derivatives. Now all of a sudden I'm asking you to do antiderivatives, and what's going to happen is your brain is going to have trouble processing it. Okay? So for instance, let me close that. What's the derivative of sine? Cosine. What's the derivative of cosine? Negative sine. Beautiful. Any problems with that? No, because you've got that burned into your brain because you've done it so many times. Giselle, what's the don't look down. What's the antiderivative of sine? Excellent. You couldn't have demonstrated it better. Thank you very much. Now you start thinking to yourself, well, wait, I know it's going to be cosine, right? So this is what you're thinking, right? I know the antiderivative is cosine, but should there be a minus sign there?
What?
Huh? You were with me up to that point, right? So the antiderivative is cosine, or so sine is cosine, but you're thinking to yourself, should I put a minus sign in front of that, or should I not? Right. That's a common mistake, or I should say a common mistake. It's a common problem. So I'm going to show you something that a professor of mine showed me in college, which I thought at the time was the dumbest thing in the universe, but I haven't been able to forget it. Okay? So, suppose I've got a antiderivative of sine, and this is how I remembered the minus sign. Okay. I'm taking, just bear with me, you'll understand in a second. I'm taking the antiderivative of sine is the exact question I asked Giselle. So the reason I made my integral symbol look like that is because I imagine this as a golf club. Okay? And with that golf club, I'm going to hit that golf ball on top of the eye. This will be really effective in the video, by the way. Okay? When I hit that golf ball on top of the eye, it travels really fast and leaves a blur. And I know that the antiderivative of sine is cosine. Okay? So, I'm sitting in a lecture hall with a couple gabillion people, and the professor goes over this, and there's an audible, what? And guess what we never missed? We never missed that minus sign from that point on, even though it was the dumbest thing ever. Okay, some of you will miss it anyway, but
Just like golf.
just an option.
Just like golf.
Especially if you're a golf guy. Please don't make your integral symbols like this. Okay.
What if the question was like that?
Well, then continue. If you're given that.
Is that the only thing that golf?
Okay, so let's try this. Go ahead, take this antiderivative. Let's see how you do. Now, stop, listen. Stop, look, listen. The nice thing about this is you have a built-in guess and check. So this group is sitting over here, and Nadia throws her iPad out in the middle and says, yo, I got it, peeps. So all Maria has to do is look at Nadia's answer and go, nah, it's not right. By doing one simple thing, what? Take the derivative, right. So if Nadia presents an answer that she thinks is right, it can easily check by taking the derivative to make sure you get back to where you belong. Are you going to do that every time you do an integral? No, but early on when you're learning the process, you may want to do that. No, I can't. You go backwards.
What a catch.
I don't like that. What do you do with the front?
He heard you say, hey.
No, he's a professional because he's in physics.
Uh-huh.
I know this like multi-time.
Unfortunately, it's wrong.
Water, natural water.
Bryce, how we doing on this one?
There we
Oh.
go.
Throw it in the center table, say, yo, I got this.
Yes.
Oh,
Dude, that's why I didn't well that one. I am doing that crap.
Excellent.
Uh-huh.
Okay, stop what you're doing. I'm gonna pick on Maria for a second. 1 over x is the same thing as x to the negative 1, yes? If we follow Luke's idea, I'm giving you full credit for that from now on, by the way. If we follow Luke's idea, we take and raise the exponent by 1. Negative 1 plus 1 is?
0.
I'm so proud. Okay. X to the 0 and multiplied by 1 over 0. You can't do it. Anthony, what's the antiderivative of 1 over x? Natural log of x. Si, senor. What did you just vapor lock there for a
I
second?
don't remember if that was in the science class. Other students just have a science.
Let's let me clear the key.
She likes the blue.
Oh, I forgot to put C.
Antiderivative is you have a variety of different types of antiderivatives. We have a general solution, general antiderivative, which is what we're going to be doing now, so yes, always a C. But we'll also take antiderivatives later on that are particular solutions. Yeah, you'll see. Give me some.
Like Carter, you throw your answer out, right?
What was your original?
Okay, so we're good to go?
What was your original? I feel bad.
No minus.
Danny, what'd you get, bud? Danny, we got it right though.
2x to the 4 minus cosine of x.
So the minus All right, let's come back together here so we can get this done. So notice, you don't have to do it this way. You don't have to do it this way. And however, early on, you might realize that you want to do it this way so you can wrap your head around it. So what did I do? I split the antiderivative of a sum and difference into individual integrals. Then I found the antiderivative of each of those parts. Okay? And what did we get for an answer, Nadia?
x to the fourth minus 7 cosine x minus a natural log. Oh, plus c.
Plus C, thank you very much. Perfect. Everybody agree? Any problems? Beautiful. Okay, so notice the 8 and the 7 don't really matter that much, just like they don't matter if you were taking the derivative. Okay, just leave it sitting out in front and then multiply by the reciprocal later. Got this? Any problems? Okay. Let's move on. Don't forget that C term.
I did.
So did Nadia. Okay, as the problems get more complicated like this, you're going to want to rewrite them. By the way, the antiderivative of 1 over x to the fifth is not the natural log of x to the fifth. Okay, so go ahead and rock that one. While you're working, I'll give you another point. Another common mistake that people, when they get into integrals, they do things like get -5 plus 1 to get -6. In case you weren't sure, -5 plus 1 is -4. That's a good start. Okay, a couple things so we can move on. First of all, the first antiderivative shouldn't have been a big deal. 12/5 x to the fifth, no problem, yes? -5, x, the cubic root of x is x to the 1/3. What's 1/3 plus 1? 4/3. Okay, multiply by the reciprocal would be 3/4. 3/4 times 5 is 15/4. X to the 4/3. We good? 1 over x to the fifth is x to the -5. -5 plus 1 is -4. The reciprocal of -4 is -1/4. -1/4 x to the -4. Yep. Plus C. This is a big issue. What is the antiderivative of P dx? Versus, easy, slow your roll. What is the antiderivative of P dP? In the first one, what's the variable?
X.
X. What is P?
Constant.
A constant. In the second one, what's the variable?
P.
Therefore, P is also a variable. What's the antiderivative of P dx? Are you okay? Do I need to call somebody? Nope. For which one? First one? So the second one, yeah. The second one is 1/2 P squared.
What? Oh, yeah. Oh, okay, we're not taking.
First one is
Yeah.
Px.
We're not taking derivatives.
Okay, that's gonna happen a lot. It's gonna happen when we start getting into word problems. It's gonna happen when you're presented with issues where you have a whole bunch of variables. The thing to remember is the dx tells you what the variable is. Anything else, whether it's a number or a letter, becomes a constant. Okay? So if it's ABC, the integral of A, B, C, D, E, F, G, dq, the variable is q. Therefore, the rest of those numbers are all considered constants. Does that make sense? Okay, beautiful. Chris?
Can you explain how you took the antiderivative of 1/x to the fifth?
Certainly. So I rewrote x to the 1, or 1/x to the 5th as x to the -5, yes? Okay, then followed Luke's rules. Raise the exponent by 1, tells me that I'm going to get x to the -4, then multiply by the reciprocal of -4, which is 1/4. Make sense?
And if you rewrote it, it would be 1/4.
That's the other thing, Chris, that Anthony just mentioned. You could, if you're feeling fancies in your fancies, rewrite this as -1/4x to the 4. Okay, so as I mentioned, these are all infinite numbers of solutions by putting a +c on the end of it. However, what if I go back to this particular picture that we had way back when? Somewhere in here. Come on, I can do it. Click, 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 click. There it is. Oh. Suppose I wanted you to solve that problem but only get one answer. I wanted just the green picture. Forget all the other infinite number of possibilities. I just want the green picture. Now all of a sudden that general solution becomes a particular solution. One possibility. So how do you do that? You have to be given some information. How are you going to steer the mathematician to getting just the green thing? To do that, you're going to give them some initial conditions. In other words, take the antiderivative of this function. I don't want to click too far here. Where are we? This is where we left off, right? Okay, so I want to take the antiderivative, but instead of getting an infinite number of solutions, I want one solution. And you do that by giving some initial conditions. Okay? For instance, I would like to know what capital F of x is. However, I'm also, so if I just stop there, you'd have an infinite number of solutions because you'd have a +c on there. However, I'm going to give you a little nugget of information there, and I'm going to tell you that f of 1 equals 0. Okay, now notice it says f prime of x equals 1/x squared, but f of 1 equals 0. So what I did is I said, what I'm asking in a mathematical way is find an infinite number of solutions, and once you have all these infinite solutions, find the one that satisfies the condition of f of 1 equals 0. In the example that I gave you before, it happened to be green. Who cares what color it is? I'm going to let you play with that for a second, see what you can come up with. I will tell you that if you do it right, you will not have a +c. because this would be a plus C, right? Stick a plus C in there. Okay, now what do you do? How are you gonna use that to get rid of that plus C? So that's the whole gist of the problem.
That's the one,
If you answer that question, you close it. And we've done this already, that should be, yeah, so, oh, don't forget, you have plus C on that one.
Oh, well, I'm saying that's equal. I'm saying it was like a negative second or then that's where you're going. So that's why I'm saying.
You're on the right track, you just did it wrong.
That's the person I was talking to,
Okay, great, yeah, so general.
Now you need to make that equal zero, minus it equals
Yeah.
zero, I think that goes like here, negative one, and then negative one.
Yeah, equal minus x. Where's the one? The only way to make it.
What do you mean?
I gotta find it. I gotta find it. You have to find them first.
When I said you shouldn't have a plus C, what I meant was your final answer should not have a plus C. You do at some point in time have a plus C in the problem, right? So walking around, what I saw was everybody that I looked at was capable of finding the antiderivative of 1 over x squared, yes? Negative 1 over x, or negative 1x to the negative first, plus C, right? We're good. So how does the f of 1 equals 0 help me? Okay,
Well, that equation just said what you got for x, so you just plug 0 equals, then you plug 1 in for x,
plug 1 in for x and plug 0 in for
f of x.
f of x or y. Solve for C,
So that equal to the equation.
and then that tells you where C is, right? Okay, so it looks something like that is your antiderivative. You all got there. Then you plug in 1 for x, 0 for f of x, and solve. And I got C to be, ooh, another slide. C equals 1. Plug that back in, and my final particular solution is that. Do you have to write it as negative 1 over x? No, you could leave it as negative x to the negative 1. It's okay. We're all friends here. Is that what you had? Or did you get lucky? Did you solve for it? Oh, then you solved it. I solved for it. I understand. You just wanted us to create this brain. I understand. Man. Just because I chose a function to be capital F. Okay. Anything else? How can we make it more interesting, Andrew? Shh. No. How can we make it more interesting? In other words, what's the next example going to be? That it will be a little harder, but what again? How could I make it harder?
C will be a big number,
Big numbers scare you?
really, really big.
Really big, like a gabillion?
Yeah.
Let's see. Nah. No. Okay. This is manageable. Go ahead, solve this one. This will be the precursor to the last problem, which will be fun for everybody. I just changed it to lowercase. It could be what I mean. You could call it K and K prime. No. While you're working, I'm going to talk a little bit. You'll see that I included the term differential equation. That's a fancy way of saying find the particular solution. A differential equation by nature involves finding an antiderivative, involves finding an integral, involves finding the general solution. Don't be bashful about busting out those calculators if you need them. Remember, you're plugging 1 in for x and setting it equal to 5, not plugging 5 in and setting it equal to 1.
Why? Why are you looking at me like that?
It's
What
wrong.
function is
I got it.
You all got 7, right? For C, 7. What'd you get for C? Okay, so before we move on to the last example, let's talk a little bit about another issue that popped up, and that is, what is the antiderivative of 7? 7x. Okay. The derivative of a constant is 0. The antiderivative of a constant is that constant times x. You should get C equals 7. Last one and then we're done. Okay, so I decided to make this one a little bit more interesting by doing a couple things. First of all, I'll just put it up there so you can start crying now. Sorry. I added 2 elements to make things intriguing. Number 1, I'm starting with an f double prime. And then, as if that wasn't enough, I threw some trig in there. You'll notice my given information tells you that f prime of 0 equals 2, and f of pi over 2 equals negative pi. So you're going to get 2 different c's. Wait, before you start, just hear me out, and then I'll let you go at it. Okay? When you take the antiderivative of f double prime, what do you get? F prime, and that will generate a c. You'll solve for that c and get f prime. Then when you take the antiderivative of f prime, you'll get f with a c. So here are a couple options that people do in the math world. Since you're going to generate a couple different constants of integration, you could call the first one c sub 1 and the second one c sub 2. What's more common, however, is your first constant of integration will be c, the second one will be d. If, for some bizarre reason, you had to do a third one, you would call that e. I'm so proud. Okay, go. While you're working, I'll put the final slide up here with a helpful mathematical figure.